Okay, so this is 5.1 and it's area under the curve. Yeah, so today we'll try to tackle something that maybe initially will seem disconnected from what we've done before. Until now, we've been mostly calculating derivatives. Right, so we have, let's do a simple derivative, just kind of show you the difference. Remind you the difference, right, between derivatives and those anti-derivatives. Anyway, so let's say we need to calculate derivative of x cubed. Right, so we did it by subtracting 1 or moving that 3 first to the front and then subtracting 1 from that exponent. Right, so if I did that, I'll get 3x squared. Okay, then I briefly showed you how to calculate antiderivatives, which was a process that's kind of inverted process of taking derivatives, right? So antiderivative. Or taking integrals, right? So let's do a quick example. So let's take a antiderivative of x squared with respect to x, right? So that's what the dx means. And yeah, as I said, the process was inverted, right? So first we add 1 to that exponent, and then this exponent, the result goes under that x to the third, right? So I have x to the third, right? I added 1, and I'm dividing by that exponent. And then we have that c, right? So plus c. Because the way antiderivative work, antiderivatives work, is that now if I take derivative of this, I should get the original function. Right? So I could add any constant to that result, and I would still get what I need to get. Okay, so that's one thing. The second thing, in geometry or in mathematics, you guys have been, we've seen, right, calculating areas of simple shapes, right? So if we had a rectangle, right, that would be area would be base times height. For a circle, area would be pi times r squared. And yeah, so if we had a just random curve, say something like this, and we wanted to calculate area under that curve or area between that curve and x-axis, right, that would seem quite difficult, and we would not know how to do it. But today I want to introduce that idea of calculating areas under a curve like you just have seen. But let's start with the simplest kind of simple curve, right? So let's do area under a parabola. So area under a parabola. Okay, so yeah, what is that? So that's y equals f of x, and that is just x squared. And of course we need to have some boundaries, right? So we'll calculate that area between a certain interval, right? So that interval will be from 0 to 4. And let me draw the situation. Okay, so coordinate system, and then from 0 to 4, and it's just that right branch, right, of the parabola. So something like this, and we have 1, 2, 3, and 4. We actually write those numbers. 1. My handwriting today is not up to speed. 2, 3, and 4. Right, and we can evaluate that function for that 1, 2, 3, 4. So this will be 1, right? Because 1 square 1, then this will be 2 squared will be 4. It's not a perfect drawing, as you can see, but I think we can use it. So this will be 9. And then for 4, I get 16. I hope it will work out. Anyway, so yeah, there are a couple of ways we could calculate. We could simply calculate the area under that curve. One of the ways will be we'll just create rectangles and then calculate areas of those rectangles. We could draw those rectangles a couple different ways. For now, let's just draw them this way. Okay, so these will be called circumscribed rectangles. By the way, let me quickly show you what area we're calculating, right? So from 0 to 4, and the area we're calculating is this one. Okay. All right, so we'll divide that area into those rectangles and simply calculate the area of those rectangles, right? It seems quite simple. Okay, so we have those points, those rectangles, and this is 16, 9, 4, and 1. I'm not going to shade all of them. Let me shade just one of them. Okay, so we'll be adding all 4 areas of 4 of those. Okay, so let me see if I can kind of squeeze it in here. Okay, so the area of the first one, let me shade that one as well. All right, so that's that rectangle, and it's gonna be, how should I write it? Let's do width. Right, so I'm talking about this distance, right? You see that all those widths will be the same, right? Those widths of those rectangles will be 1, right, in general. So it's going to be 1 times the height, right? So I just showed you base times height. Right, so height, in this case, is this distance, and it's 1. So it's going to be 1 times 1. Okay, then we have the second rectangle. That base or that width is still 1. Right? Didn't change. So it's going to be 1. At this time, the height, right, is 4. Right? I'm talking about this rectangle, and the height, see, it's 4. So it's going to be 1 times 4. And then another one, right? So again, the base, the width, is 1 again, and the height is 9. Plus 1 times 16 times 16. Okay, so yeah, that's not supposed to be z. It looks like z. Now we're just going to add it up, and we get equals 30 units. Okay, so this is a pretty kind of rough estimate, right? It's not exactly the area under that curve. But that's just one of the way to do it. Another way would be to maybe draw a smaller picture. Would be to inscribe those rectangles, right? So I would have that curve again. 1, 2, 3, and 4. So now when I'm drawing those rectangles, right, I have the same points. Right, so for 1 I get 1. For 2 we get 4. 3, 9, and for 4 we get 16. Right, but this time I'm inscribing, right? So those rectangles will be under the curve, right? So something like this. The first one is just gonna be 0. Okay, then the second one, right, and the last one is supposed to go to 4. Okay, so this time you can see, well, that the area of that of that of those rectangles, of that sum, will be less than the actual area under that curve. And then, the last thing, if we kind of follow the same concept, the same idea, we could maybe pick the midpoints. Okay, what do I mean by those midpoints? So again, right, so we have the curve. So 1, 2, 3, and 4. So I'm taking, right, I'm not inscribing or circumscribing those rectangles. I'm picking up those midpoints between and in those distances. So this is going to be 0.5. This is 1.25, etc., etc., right? And then we could come up with those heights. The first one is 0.25, right? I'm squaring those 0.5. Let me actually draw those rectangles first, right? So first one, right, that height line will go through that midpoint, right? So that's gonna be the first rectangle. Then the second go here, and then midpoint will be here. Okay, and the last one here somewhere, right? Okay, so I hope you understand the idea, right? It's not a perfect picture, but I hope, yeah, it kind of illustrates what I'm trying to explain. So 2.25, right? And then that last height is 12.25, I think. Right, so if we add these areas, right, the distances, the base kind of is the same. And if we add these up, I will get 21 units square. This one will give us 14, by the way. Right? So this is probably the best estimate, right, of them all. Okay. Yeah, so we could, right, we could I could show you, right, this calculation, but let's focus on this particular calculation, because I have it written down over here, and we see that, right, I'm multiplying those heights, all of those heights, multiplying them by 1, right, by base. So this, I'm going to call that base delta x, and I will factor it out. Okay, so like this. So that 1, now let me just kind of, right, show you that. So that's that base, and here I have, right, this 1 plus 4 plus 9 plus 16. I should have written it. Let me write it a better way, nicer. Okay, so that width is 1, and then we have those heights, 1 plus 4 plus 9 plus 16. Okay, so now let's make it more abstract. So that distance, that width, right, I'm talking about this width, I'm going to call it delta x. Okay, so we'll have delta x. And now, instead of writing 1, I will write f of 1. Right, so it's going to be f of 1 plus f of 2. Right, so that's what those heights, how I got those heights, right? F of 3 plus f of 4. Okay, so eventually, finally, right, after kind of, this is a sum, right? So I hope you're familiar with this symbol, and I will explain what this means, how it works in a moment. But I'm going to express this sum using this symbol, the summation. So right, it's going to go from 1 to 4. And it's going to be f of x I. Okay? So this simply is it actually is not, how should we do it? Maybe it's not like this. It's more like this. Okay, so that's that sum of those heights. And now I still have that delta x in the front. Okay, so I have okay. My writing today, as I said, is just not. Okay, delta x. And when we're dealing, this delta x will always be kind of constant. And we can take that constant and put it kind of back in here. Right? So I'll just move it here. So finally, we'll be dealing with something like this. So I have the summation from I equals 1 to 4, f of x I. So suddenly, right, something that was quite simple became quite complicated, right, because of that notation. So let me explain that notation a little bit. Okay, so notation. Hopefully you've seen a little bit of it in maybe pre-calculus, I'm not sure. Anyway, so if I have, let's say, I have a sum from, right, we'll have 12 elements from 1 to 12. Right, in our case we had 4 elements. Here I have 12. And I'm just going to be adding 3. Okay, so that is going to look like this. So I'll have 3 plus 3 plus 3. And I will be adding that 3 12 times. Plus 3, right? I'm not going to write all of those. So 12 times. Right? I'm adding those 3's 12 times. So I could simply write it as 3 times 12. Or 12 times 3. 12 times 3. Okay, so in general we could write it like this. Right? If I wanted to add some number c, let's say, n times, so sum from I1 to n, right? I'm just making it more general, n times c. Okay, so if I wanted to add 2, right, so that 2 will be c, and I don't know, 64 times, that would be, n would be 64, right? So 64 times 2, and you get 128. Okay, so, but our example looks a little more complicated, right? And let's introduce, I hope you guys know what integers are. So, yeah, we'll be dealing with integers mostly, and adding them. Well, not really integers, but okay, so let's think about adding integers. Let's say we want to add, I don't know, 16 integers from 1 to 16, right? So that would be, I would take 1 plus 2. That's what I mean by adding integers, right? Plus 3 plus 4, right? All the way to 16. Okay. So the way we would write it would be something like this, right? So I would go, I goes from 1 to 16, right? And I would put that I here. And then we just write it 1. Just the same way as we did over here. 1 plus 2 plus 3, right, all the way to 16. And yeah, we could add those, right, n number. We could add any number of those integers we want, right? And the way we would write it would be like this. So I have, let's start with 1 and with n, and then I'd be adding n integers, right? So 1 plus 2 plus 3 plus etc., right? We'll have n of them. And then normally there's a formula, right? And in calculus 2 you will learn where this formula comes from. But if I have, I don't know, say 251 integers that I want, first integers that I wanted to add, right? And it would take quite a long time. So we have a formula for it that looks like this. This is just a parenthesis. And it's over 2. Okay, so there are different, of course, we could call them functions, right? That we could apply to those integers, and we could square them. Right? That'd be our case actually. Right? So if I have I squared, right, so I'll be adding 1 squared plus 2 squared plus 3 squared plus, right, etc. And the formula for that, again, right, we'll see how it was derived. Calculus 2, so n plus 1. Hope I have more space. I don't. So let me make it a little shorter. Usually 3 dots, right? It's kind of the industry standard. So formula for that, and because again, right, we don't want to be adding a lot of numbers, so we have a formula for it, plus 1 and plus 2 divided by 6. Okay. So now let's go back to our area problem. Okay, so, and again, right, we'll try to make it more abstract, or I will. Right, so again, we still have the same curve, right? So y equals x squared. This didn't go anywhere, but this time, let's what we'll make more general is that we won't be calculating it between 0 and 4, but between a and b. Okay, well, yes and no. Okay, so this is the area we're interested in, and I hope you understand that, right? The more of those rectangles we have here, right, the more accurate our result, the area that we calculate, will be, right? So we can have, well, n rectangles. Okay, so if I have n rectangles, then this one of those distances, right? So the distance between those points, or between those tick marks, right, will be the delta x. Right, will be that the whole distance, right? So from here to there, right? To calculate this width of one of the triangles, one of the rectangles, will be taking this distance and dividing by how many of them we have. Okay, that B kind of disappeared here, and I don't like it, so that's B right there. Okay, so that's going to be B minus A, right? So that's going to be the distance between B and A, and then divided by how many rectangles we have. So in our case, we'll have 4 minus 0 divided by n. Right, so that's going to be 4 over n. Okay, so far so good, I hope. All right, so now let's go back to that. Right, we had this formula for that area. Right, it looked like this. So let me write it here. It's right. So that area was, we had the delta x. Now I'm adding those, right? F of 1. So now I'm calculating, or I'm kind of still focusing on that 4, right? Where B is 4, and we're calculating the area between 0 and 4. Right? So I'm doing F of 1, F of 2, F of 3, F of 4. Okay, so now instead of writing that F of 1, F of 2, right? Let's make it more general, kind of still keeping that distance from 0 to 4, but now making the number of those rectangles equal to n, right? So n, the number of the rectangles, right? So it's going to look like this, right? So the first one will be f of, or actually, let's just kind of keep it as that 1, 2, 3, 4, right? For now. So it's going to be 4, f of 4, right? That first number, 1, right? To get that 1, I will have 4, right? Times 1 divided by n. Right? N, again, is 4, right? So 4 divided by 4 is 1. So I will have that 1, right, that I need. Okay? The second one. Plus, this time it's going to be f times 4 times 2, right? So 4 times 2, right? I'm just kind of trying to, I hope you understand what I'm doing. I wonder if I can move this. Let me try to move it. Okay, I did succeed. Okay. Right, so I'm just rewriting. This is, right? I hope you see that this is still 2, right? So because I'm still kind of limited, I'm limiting myself to number of those rectangles being 4. Okay, so that n is equal to 4. Okay. Now the next one, f, again, right? So 4 times 3 divided by n. And I ran out of space again. But yeah, you get the idea, right? So 4 times 4 divided by n. Okay. Okay, so now you see this 1, 2, 3, and 4, right? So that's going to be our I, right? So now if I write it in a more, again, more general form, right? So that delta x is going to be in front. Now I have that sum. And I'll have I I go from 1 to 4 technically, but let's actually make it more abstract again. Okay, so I have those sums of 4 times I, or 4I divided by n. Okay, and now our function is, right, f of x is x squared. So this actually will be squared, right? To get those heights, right? I'm kind of evaluating those functions for those numbers here. Okay. Yeah. So basically, kind of the rest is algebra. So we have that area. Right, it has that summation from 1 to n, and then we have 4I over n squared, and I'll take that delta x, and this delta x was, I believe, 4 over n, right? We have it here. So I will put it in the back, so delta x, or 4 over n.